Hello, students! So this video here and this lesson is about isosceles and equilateral triangles. So in our most recent and latest lessons, we discussed the triangle angle sum theorem, which discusses the relationship that the three interior angles in a triangle has. The fact that all three interior angles in a triangle add to 180 degrees. And we discussed the exterior angles theorem, which tells the relationship that an exterior angle of a triangle has with its two remote interior angles, and the fact that the exterior angle is equal to the sum of those two remote or opposite interior angles. But again, folks, in this video we're gonna go and get into isosceles triangles and equilateral triangles. Now, some of you might be familiar with these terms. I'm sure you've heard of them before, maybe middle school, maybe elementary school. But again, folks, we're going deeper into them. And so let's go ahead on and get started. Let's give you some information that you're going to need to know about these. So, folks, when we talk about isosceles and equilateral triangles, these particular names are types of names that we give to triangles based on classifying triangles by their sides, or classifying triangles by their side lengths. And folks, there are three different classifications that we use for triangles when we're classifying triangles by their sides. Those three classifications, or the main three that we use, are scalene, isosceles, and equilateral. Again, folks, most of these different classifications of triangles you've probably already heard of. But again, let's get into it. A scalene triangle is a triangle that has no congruent sides. So again, guys, if it has no congruent sides, that means that it has three sides with different lengths, right? All right, so that's a scalene triangle. An isosceles triangle is a triangle that has at least two congruent sides. So when we say at least two congruent sides, we mean that it has two or more sides with the same length. All right, and so that's an isosceles triangle. And then an equilateral triangle is a type of isosceles triangle that has three congruent sides. So when I say that it's a type of isosceles triangle, okay, what that means is that every single equilateral triangle, every equilateral triangle is also an isosceles triangle, because equilateral triangles are a type of isosceles triangle. Now, is the opposite of that true? No, definitely not. No, every isosceles triangle is not an equilateral triangle. Okay, and that's why it says here that isosceles triangles have at least two or more congruent sides, meaning that it could have it could have two or more sides with the same length. At least two congruent sides. All right, but anyway, folks, those are the three classifications of a triangle by its sides and by its side lengths. All right, so folks, something that you want to make sure that you know when you're looking at a diagram or drawing an actual, like one of these types of triangles, isosceles or equilateral, you want to make sure that on the diagram or on that triangle that you're drawing, that you see certain indications on that actual picture or diagram that let you sure enough know that it's an isosceles triangle or an equilateral triangle. So, folks, you'd want to definitely see, like, either you'd want to actually see congruency marks, like what you see on these diagrams over here, the little tick marks that that are our congruency marks for the side lengths or for the sides of a triangle or for the sides of any polygon really. But again, those little congruency marks there, you want to make sure you either see those little congruency marks like that are matching on those congruent sides, or folks, you want to actually see like the actual same side length written in. Like for instance, if that side length was 8 inches, and then you'd want to see that this side was also 8 inches, right? That lets you know that it has two sides that have the same length, or in other words, that it has two congruent sides. And if that's the case, then it's an isosceles triangle, right? And so again, I'm going to erase that, but again, I think you get what I mean when I say make sure that your diagram has those certain indicators up there, either the congruency marks or those actual side lengths written in that lets you know that the two sides are the same length, or in other words, that the three sides are the same length if it's equilateral, or you're going to want to see the congruency marks. So again, either congruency marks or those actual side lengths, the same side lengths need to be shown or written in the diagram or picture. Okay, so let's take a closer look at equilateral triangles. All right, so guys, again, we said that an equilateral triangle is a type of isosceles triangle that has three congruent sides. Well, folks, an equilateral triangle is the smallest of all regular polygons. For those who are wondering what a regular polygon is, a regular polygon is any polygon that has all congruent sides and all congruent angles. So again, we've got the smallest type of polygon, which is a triangle, and a regular triangle would be your equilateral triangle, which has all three sides that are congruent and all three angles that are congruent. So your equilateral triangle is a regular triangle, okay? We refer to it as a regular polygon or a regular triangle because it has all congruent sides and all congruent angles. The same way, folks, that a square would be considered a regular quadrilateral. Yeah, that ain't what I meant to draw. I was trying to put that there where it looked like it actually had all four right angles, but y'all know that. All right. A square would be considered a regular quadrilateral because it has four congruent sides and four congruent angles, which are all right angles. So a square would be considered your regular four-sided polygon or a regular quadrilateral, the same way that an equilateral triangle would be considered a regular three-sided polygon, which we know is a triangle. Okay, all right, I'm going to erase this square here, but again, that's what the word regular means. If there was anyone who was wondering that. All right, so a equilateral triangle is the smallest type of regular. Where am I at? It's the smallest regular polygon. Yeah. Let me get rid of this here. Y'all excuse me for a moment. Okay, so guys, here's the deal. Here's the deal. If an equilateral triangle is a regular polygon, what that means, folks, is that all equilateral triangles, because they're regular, they have all congruent sides and all congruent angles, all equilateral triangles are also equiangular. So, guys, that classification that you see there, equiangular triangle, that means, and it should be clear by the way that word looks, as in equal, equal angular, right? All of the angles are equal in that polygon, right? So equilateral triangles, all equilateral triangles will also be equiangular. So folks, you won't see oops, thought I was drawing. You won't see an equilateral triangle where all three sides are the same, like if that was 4, 4, and 4, right? You can't have an equilateral triangle without having all of the angles be congruent to each other. All three angles are congruent in any equilateral triangle. And guys, the opposite of that is also true. If you know that you've got an equiangular triangle, and if you know that all three angles are congruent, and first off, guys, let me make this point here. All right, so by now, since we've gone through the triangle angle sum theorem, by now you should know what the three interior angles of a triangle add to, or you should know that all three of the interior angles for a triangle add to 180 degrees, that they're a total of 180 degrees as far as those three interior angles for any triangle. So if you know that all three angles combined add up to 180 degrees, folks, if all three of these angles have equal measures, or in other words, if the triangle is equiangular, right, what happens if you divide all of those degrees by 3, right? So for any equiangular triangle, each of those angles is going to have to be how many degrees, right? Split 180 3 ways evenly. There's your answer, right? So for any equiangular triangle, each angle is clearly going to have to be 60 degrees. 60 degrees, 60 degrees. Yeah. I know I'm writing that on the outside of that triangle because I don't have a whole lot of space to write it on the inside. But we know that we're talking about the interior angles there, okay? I don't have any exterior angles drawn. I didn't extend out any of these sides. So if you can't make that out as the three interior angles, I don't really know what to tell you on that one. But anyway, yeah. So guys, any equilateral triangle will also be equiangular. And folks, if we know that it's equiangular, it has to be equilateral, and each angle has to be 60 degrees. If it's equiangular, if the triangle is equiangular, each angle has to be 60 degrees. Yeah, that one didn't quite look at the way I wanted to look. Yeah, that's a little bit better. Not really, but it'll work. So again, guys, that's something that's pretty special about equilateral triangles. That you need to know, that you will need to know and use. So again, folks, whenever you see an equilateral triangle, a triangle that has a triangle that has all three congruent sides, or three sides with the same length. Whenever that's the case, folks, all three of the angles, even if it's not marked in the diagram, it's still true. Whenever you've got an equilateral triangle, all of your angles in that triangle will be the same. An equilateral triangle is always equiangular. And guys, the opposite of that is true as well. Whenever you have an equiangular triangle, where all three of the angles are the same in a triangle, and we know that when you do have an equiangular triangle, each angle will be 60 degrees. So when you do see an equiangular triangle, folks, even if it is not marked, when you have an equiangular triangle where each angle is congruent, or in other words, where each angle is 60 degrees, what that means is that all three of the sides for that triangle are also congruent, even if it's not marked on the diagram. Okay? Equilateral triangles are equiangular, and equiangular triangles are equilateral. Okay? Alrighty. I want to make that very clear. Okay, so folks, next we're going to look a little bit closer at isosceles triangles and some of the different components, some of the different components to isosceles triangles and what those different parts are labeled and called, and then we'll talk about a theorem that's involved with isosceles triangles. Now again, the information that we just now looked at about equilateral triangles is technically a corollary to, don't focus on that big word that I just now said, but it's technically sort of like another theorem that I just told you about equilateral triangles, but it's a corollary to a theorem about isosceles triangles. But anyway, folks, next we're going to look at isosceles triangles, and we're going to talk about those different parts of that, and we're going to look at that theorem involved with isosceles triangles. All right, so folks, here we go with isosceles triangles. There are certain parts that you need to be able to recognize, and that you need to know what the names of these parts are before we talk about that certain theorem that has to do with with isosceles triangles. All right, so folks, in an isosceles triangle, the two congruent sides are called legs. Okay. Folks, don't get that confused with when we talked about right triangles. When we talked about right triangles, and I know that looks very, very sloppy. Don't get that confused with when we talked about right triangles and how we talked about that those two sides of a right triangle that form that right angle. Those two sides of the right triangle that form that right angle were referred to as legs, and the third longest side of the right triangle was called a hypotenuse. Don't get it twisted. Even though it has the same name, folks, this is a different context that we're using leg in. Okay, so it's different when we're talking about the legs of a right triangle, which are again those two legs that form the right angle that come together to meet to form that right angle. Is different when we're talking about the two legs of a right triangle. I'm going to go ahead on and erase that, because that's not the context that we're using legs in. Oops, I thought I was erasing. Give me one sec. All right, so I'm going to erase that. Now, I don't want y'all to be confused. Well, Mr. Chucky, we've heard you say leg before. Well, we're not talking about the legs of a right triangle right now, okay? So, in an isosceles triangle, the two congruent sides are called legs. Okay, so whatever those two sides are that have the same length, or those two sides that are congruent, those two sides are going to be referred to as the legs of an isosceles triangle. Folks, the third side in an isosceles triangle, and what I mean by the third side, that one side that's not one of those two legs. The side that's not one of those two congruent legs, okay? That's not one of those two congruent sides. That third side is always called the base of a right triangle. Now, folks, I'm going to go ahead and tell you, some of you are going to not, I sincerely hope that is not the case. But some of you might disregard what I'm telling you here, and some of you might always assume. Some of you guys might always assume that the base, because of the way that the word base sounds, some of you might always assume, which would be wrong, some of you might always assume that the base of an isosceles triangle is always going to be that side that's at the bottom. Not true, folks. That is not the base of an isosceles triangle. Not necessarily. Okay? Please pay attention to what I'm saying, because if you don't, you're gonna be all messed up. Okay? And it won't be because I didn't try to tell you. Please do not assume that the base of an isosceles triangle is always the side that is at the bottom, because that is just not true. All righty. You heard me, right? Did you hear me? I said, you heard me. All righty. All right, so the base of an isosceles triangle is going to be that side that is not the two legs, okay? And it does not have to be the side that's at the bottom of a triangle. You can have a triangle looking so many different ways. I ain't even got to even try to. I mean, and now that mess there, it's just making my triangle look like that. Okay. Like I said, folks, it does not have to be the side that is at the bottom. It just depends on where your two congruent sides are for an isosceles triangle. But again, folks, you see right here, if these are the two congruent sides for this isosceles triangle, that means that these two sides are technically the legs, right? Leg and a leg. So, folks, what am I saying? For this triangle that I've drawn right here, this side that's at the bottom of that triangle is not a base. That the side that's at the bottom of this triangle that I've got selected right here, the one that's drawn in red, is not a base at the bottom, as I'm trying to tell you right now. But again, the base of this one would be that third side that is not one of these two legs. Okay? So again, please pay attention to that. All righty. Okay, because I'm trying to be pretty thorough here, even if it means taking up a few extra seconds or possibly 1 extra minute in the video. I want to make sure that I'm thoroughly explaining this to you, so you don't have any excuse to not know what it is that you need to know. Now, you can always contact me if there's something from here that you don't quite understand, but I don't want you to have any excuse for you not to know. You won't be able to say to Mr. Starkey didn't try to let you know. All right. Okay. All right. So again, folks, that's the base of an isosceles triangle. And folks, the two angles that are formed by the base. Okay. So the two angles that are formed by that base. So you see that base in this triangle, this black triangle that I've got right here. The two angles that are formed by that base and its adjacent sides are considered the base angles. Excuse me, are considered the base angles. They're called the base angles. These two angles right here, that one and this one. And again, folks, they're going to be called base angles. The two angles that are literally right there, formed by the base of your isosceles triangle. Those are going to be your base angles in an isosceles triangle, and that's what they're called. And guys, the third angle, and you should know what I mean when I say the third angle in an isosceles triangle. When I say the third angle, I'm talking about that angle that is not the two base angles. Okay? So the third angle, the one that's not the two base angles in an isosceles triangle, the third angle, which is opposite of the base. And when I say opposite of the base, I mean that third angle that is the farthest from, or that third angle that is directly across from the base of the triangle, of this isosceles triangle. So you see the position of the base of this isosceles triangle, and guess what? Okay, you see how the two base angles are the two angles that are the closest to that base, and you see how the two base angles are literally the angles that are formed by the base and its adjacent sides, and you see directly across from that base. Okay, I'm going to erase this afterwards, but directly across from that base, and the farthest away from that base is that vertex angle. Okay, so that's the angle that's opposite from that base. and it's called the vertex angle. Okay, again, like I said, I'm erasing that little green arrow I just put there. Green arrow. Green arrow. He's a superhero, even though he ain't really got no superpowers. I mean, he's good at archery. I mean, he could. Anyway, green arrow. Okay. So again, folks, these are those different parts, those different components of isosceles triangles, and you need to be able to recognize them and know what they are, know what they're called, right, and everything like that as well. So, folks, we've got the legs, which are the two congruent sides in an isosceles triangle. We've got the base, which is that third side that's not the two legs, right? And then we've got your two base angles, which are those two angles which are that are the closest to the base and that are formed by the base and its adjacent sides. And then guys, we have that third angle in an isosceles triangle that is opposite from that base, or in other words, it's the farthest from that base and directly across from the base. And that third angle is called the vertex angle. So, folks, next we're going to look at a theorem that is used to describe the base angles, or really it's called the base angles theorem. But again, folks, it's a theorem that is specific, very, very specific to isosceles triangles, because again, folks, we don't have base angles. As far as I know, we don't have base angles in other types of triangles. Now I'm not sure if there are base angles in other types of polygons, but I know, as far as I know, that they're not base angles in other types of triangles. All right. So anyway, folks, we're gonna look at the base angles theorem, which is only something that happens or something that applies to isosceles triangles. Okay, base angles theorem coming right up. Okay, so folks, the base angles theorem. This is a theorem that pretty much it only applies to isosceles triangle, or at least we'll only be using this theorem with isosceles triangles. And again, folks, what the base angles theorem says is this: if two sides of a triangle are congruent, well, guess what? What do they mean if they say if two sides of a triangle are congruent? Well, we know the only type of triangle that has two sides that are congruent, the only type of triangle that they could be talking about is isosceles, right? So when they say if two sides of a triangle are congruent, what they're pretty much saying is if a triangle is isosceles, I'm paraphrasing. I'm going to erase what I'm writing here, but I'm paraphrasing here, right? If a triangle is isosceles, that's pretty much what they're saying. If two sides of a triangle are congruent, right? So in other words, if a triangle is isosceles, okay. All right, so if two sides of a triangle are congruent, then the angles opposite of them or opposite to them are congruent. Well, guess what, folks? The only I thought that was going to look like an actual triangle. Okay, better a little bit. So guess what, folks? The only types of angles that are going to be opposite of your legs. So again, when they talk about the two sides that are congruent, the only angles that are going to be opposite from those legs, as in like far from those legs and directly across from each of those legs. Yeah, I thought I was making that straight. The two angles that are going to be directly across from and the farthest from those two congruent sides or those legs are, of course, guys, your base angles. So what they're saying is that if a triangle is isosceles, if you are certain that a triangle is isosceles, then what must be true is that those angles that are opposite of those legs, in other words, your base angles, then the base angles must also be congruent. So in other words, if you've got two congruent sides, two congruent legs, meaning that your triangle is isosceles, then folks, the base angles, yeah, I know that's sloppy, I apologize. Okay, then folks, the base angles must also be congruent. Then those two base angles are also congruent. I'm paraphrasing, and I'm about to erase that. All right, so again, folks, that's pretty much what this base angles theorem is. What this base angles theorem is saying, that if two sides of a triangle are congruent, and you know we're talking about the legs of an isosceles triangle there. So in other words, if we got an isosceles triangle with two congruent sides, which are called legs, right? So then the angles that are opposite of those two congruent sides, or in other words, we're talking about the two base angles, must be congruent. Okay. All right. So that's what the base angles theorem says. And again, officially, it says if two sides of a triangle are congruent, then the angles opposite to them are congruent. Again, that's an if-then statement, of what we call a conditional statement. I don't really have time to go into conditional statements, but anyway, folks, that's the base angles theorem and what it says. So again, folks, one way that it could be written is like using expressions. Instead of it being written out like in words like that, it could be written out in expressions. For instance, given triangle ABC. So given that we have a triangle ABC, if AB equals AC. So in other words, when we say AB and AC, we're talking about the length of side AB equals the length of side AC. So in other words, they're saying that you got two congruent sides, two sides that are the same lengths, right? So they could either write it like that, where they say if the length of side AB is equal to the length of side AC, or guys, they could write it out using the congruency symbol, and they could say if side AB or segment AB, which is side AB, if segment AB is congruent to segment AC, so again, they're talking about, again, those two congruent sides, so same thing. So if you've got two congruent sides, or two sides whose measurements are equal, okay, and that's what they got there, then, folks, those opposite angles for those two sides, or in other words, those base angles, are going to be congruent. So the measure of angle B equals the measure of angle C. And again, another way that it could be written is using the congruence symbol that looks like an equal sign with a little squiggly mark over it. Okay, all right, equal sign like with that little squiggly mark on top of the equal sign. That's a congruency symbol, and I've shown you in a previous lesson as well. But again, folks, that's the base angles theorem. Okay. So guys, so that's the base angles theorem, and folks, look, the opposite of the base angles theorem and what we in math call the converse of the base angles theorem, the converse of that conditional statement. Anyway, I ain't got time to go into all that. But the opposite or the converse of that base angles theorem is also true. And let me explain what I mean. So, folks, the base angles theorem says that if you have two congruent sides in a triangle, then those base angles are congruent. So the opposite or the converse of that is also true. Okay? So something that's also true The converse of that, which is also true, okay, give me a sec, y'all, was also true, is that if two angles of a triangle are congruent, yeah, okay, I thought I was writing that. There we go. There we go. Okay, now I got a little bit more space to actually finish what I'm writing there. If two angles of a triangle are congruent, so what are they talking about? So now they're saying if you got two, and I'm letting you know that this is also true, folks. That if you got two congruent angles in a triangle. And if you know that you've got two congruent angles, so if you know that two angles in a triangle are congruent, what's also true is this, that the sides that are opposite of them, that the sides opposite of those two congruent angles are congruent. The sides opposite to them are congruent. Okay? So it works both ways, folks. It works both ways. Both ways. Yeah, that ain't exactly how I needed it to look, but guess what? If I put my little congruency marks here, it don't matter how the triangle look. It sure don't, because if I put my little congruency marks there on this side, guess what? These two sides are congruent. So it works like this. If you know the two sides are congruent, and so I'm gonna do it not using those congruency marks, but I'm gonna do it with side lengths. So if you know that these two sides are congruent, 8 feet and 8 feet, right? It's an isosceles triangle. So if you know that, that means that these two sides that are opposite from those, so that the two base angles, or those two angles that are opposite from those two sides are congruent. Right? That's what that means. This part here. So these two base angles. Okay, yeah. I didn't want it to look quite like that. I did, but I didn't. Give me one sec. There we go. A little bit better. Okay, so we know that if we got two congruent sides, the base angles have to be congruent. And then I'm gonna, again, folks, the same thing is true if we've got oops, give me a sec. If we got two congruent angles, the same thing is true. So I'm gonna go ahead on and put here, like if we got 40 degrees right here, and if we got 40 degrees right here. I told y'all it don't matter how the triangle look. If the information is there, then it's there, okay? So if we got two congruent angles, whether it looks like an isosceles triangle or not, it's an isosceles triangle, okay? So we got two congruent angles. That means that these two are technically base angles. And if you've got two congruent angles like what you see right here, that means that the sides, that those two sides that are opposite of those two of these two angles. So they're talking about these two sides that are opposite of these two angles. This one, and yeah, I wish I didn't. It's all good. And yeah, hold on. Let me put this one first then. This side. Wait, that ain't what I'm trying to put. Hold on. There we go. This side and this, yeah. Try not to make it look too sloppy, y'all. And this side, there we go. A little bit better. Have to be congruent. Put my little congruency mark. Yeah. Okay? So that's how that works. The base angles theorem And then the opposite of that is also true, the converse of the base angles theorem, which I ain't really got time to go into, talking about conditional statements and their converses, their inverses, their contrapositive. I don't have time to talk about all that because that'll take another 10, 15 minutes to explain that to you. But anyway, folks, that's the base angles theorem. Folks, we're going to look at a few examples. A few different examples to show you how some of these different problems could look when we're dealing with not only just equilateral triangles, but also with isosceles triangles. All right, so again, folks, we're going to look at some examples next. Yeah, I had to erase all of that writing over there that was real sloppy. Yeah, I didn't like the way that looked. Anyway, we're going to look at some examples next up. Yeah. All right. So let's look here at example 1. All right, so here it says find the value of all the variables. Okay, so with this, folks, you can see here, now, guys, the practice that I've got you doing, I'm asking you to show your work. One thing that I'm going to sure enough need you to do is to first off state what type of triangle you got here. Okay, like if it's an isosceles triangle, state that it's an isosceles triangle. If it's an equilateral triangle, state that it's equilateral. You know. All right. So yeah, the first thing I'm needing you to do is do that right there for me. Okay. All right, so here we got an isosceles triangle. All right, and we know it's isosceles because we got two congruent sides, right? Okay, so folks, the only thing that we've been given here is that angle measurement of 125. Uh-oh. Y'all see that? Y'all see that? That's an exterior angle in this triangle. Y'all see that? Well, I tell you, boy, well, you can't take nothing for granted, can you? I mean, we literally just now got finished talking about exterior angles. That was our latest previous lesson that we just did. And look at what's in there. You see that? That's an exterior angle of that triangle. Anyway, folks, so we've been given the measure of this exterior angle of 125 degrees. And so again, folks, what we talked about as far as exterior angles go, the relationship for an exterior angle is for this particular case, an exterior angle and its adjacent interior angle are always going to be linear, always going to form linear pairs, which means that those two angles right there are supplementary. All right. So again, folks, these are supplementary angles. This exterior angle and its adjacent interior angle. Those two are a linear pair, which means, again, that they're supplementary, which means that they add to 180 degrees. I ain't going to put all of that, but again, they're supplementary, which means that they add to 180 degrees. Okay? All right, y'all see that right there? I'd like for you guys to put the reasoning behind how you know, and how you're finding these parts as well. So, like, because honestly, you're not going to be able to get what x is if you don't know that 125 plus x equals 180 degrees. Honestly, you're not going to be able to do that. So, the reasoning behind this I'm asking you to write out your reasoning. Again, folks, you need to know what's going on to be able to even work these out. And that way I can see what you're doing as well. All right. Okay, so linear pair, they add to 180, which is how we getting what x is, of course, right? So that's 125 plus x equals 180. We don't have to actually show. We don't have to actually. Well, I'm not about to show working that out. Again, I'm asking y'all to show y'all work when y'all do y'all's practice assignment for this lesson. And of course, guys, we know that x would have to be 55 degrees. X would have to be 55. So this angle right here, of course, would be 55 degrees. Alright, so in your type of triangle, your reasoning behind everything. I need to see your reasoning. I need for you to put your reasons for how you were able to come up with certain things. Because I mean, all of this stuff right here is there's a reason why x equals 55, and you need to know. I mean, I'm writing it out, and you got to know in order to do all of that. Okay, so that's all I'm trying to say. I need for you to write it all out when you showing me your work. That's all I'm saying. All I'm saying. All right, so x is 55 degrees, folks. The next little reason of things that we got going on here. Of course, the first thing as far as reasons was the fact that we had that linear pair there, those two angles that were forming a straight line. The next thing, guys, is because we've got those two congruent sides, we can use the base angles theorem. Okay, so your base angles theorem. Which lets us know, again, folks, that if we got two congruent sides, that those base angles, or that those angles that are opposite of them, have to be congruent as well. Right? So your base angles theorem. Oh, yeah, that's sloppy. All right. So again, folks, I'm not expecting you to write out the definition for base angles theorem, like if you're giving me base angles theorem as your reason, but I do want you to write out like base angle theorem. You get what I'm saying here? I want you to write out base angle theorem. Okay. Now I'm writing out the definition, so because I'm explaining this stuff to you, and I need for you to remember what the base angle theorem says. Yeah. Okay. That's why I'm writing this out. If two sides of a triangle are congruent, then the angles opposite to them are congruent. Ooh, that's sloppy. But it'll be all right. It's going to have to be all right. So they're talking about those base angles. All right, so again, what does that mean? What does that mean? That means that since we got, that is the sloppiest thing ever. Oh, better. All right, so that means since we got these two congruent sides, let me make that a little bit smaller. Yeah. All right, since we got these two congruent sides, that means that those two angles that are opposite of them, or in other words, those two base angles, right here, are going to be congruent to each other. My little congruency marks right there. All right, and I'm going to put that in the original diagram because that's true because we know what the base angles theorem says, right? So again, if we got two congruent sides, those two congruent legs, that means that the base angles for this isosceles triangle will also be congruent. So again, so if one of those angles was 55 degrees, that means that the other one is 55, right? So this is 55, this one is 55. So what that means? That means that Z is 55. All right, so right now we got X. We got Z. Okay. All right, next up, let's find out what Y is, right? I need you to put your reasons up there. I need to know that you know what you talking about. Okay? You know what I'm saying? I need to know. All right, so here, the only way that we're going to find Y in this, well, there's two different things that we could do to find Y. You could either use the exterior angles theorem, or you can use the triangle angle sum theorem. It's up to you. I'm going to use the triangle angle sum theorem. I know what that says. Not that I don't know what the exterior angle theorem says. So my next reason that I'm using to find out my next part is the triangle angle sum theorem. Now, folks, us putting these reasons here, there's a purpose for it. They'll like you might see somewhere in your future, in your near future, whether that'll be somewhere during this class or in your next class, where you may have to write out proofs about certain things, where you'll be expected to list out your reasoning for everything that you do. So but anyway, that's why I'm showing what I'm showing right now. That's all I'm trying to say. All right. The triangle angle sum theorem, again, folks, with you listing out your reasons for me, I don't expect for you to state what the triangle angle sum theorem says as part of showing your work, because you should know what it says. But again, I'm gonna write out what it says to remind you of what it says. Okay. Well, this one ain't really if, but it could be written as an if-then statement, but I'm not going to write it as an if-then statement. All three interior angles of a triangle add to 180 degrees. That's our reasoning that we're going to use to find Y. And it's true. Oh, it's definitely true. All right, but yeah, that's the reason that we're using to find Y. Okay? All right, so again, all three interior angles, let's go. Let's do it. Let go, let go, let go, let go. Let go my ego. Okay. All right. So let's see here. 55, 55. All right. So X plus Y plus Z. All three of those interior angles have to add together to equal to 180. All right. So we had already found that X was 55. We had found that Z was 55. And the only thing that we need to find here is Y. Right? All right, and so again, 55 plus 55 is 110, 180, and to subtract 110 from both sides, and we get the Y equals 70, right? Okay, great. Y is 70. Okay. All right, so again, folks, when you're showing your work, for me, for the practice, for these practice problems, I need for you to state, first thing, I need for you to state what type of triangle it is. If it's an isosceles triangle, and I mean if it's an isosceles triangle and it's not equilateral, as well, then you'll say that it's an isosceles triangle. Of course, if it is equilateral, then you don't have to say that it's isosceles, because we know that an equilateral triangle is a type of isosceles triangle. Anyway, folks, that's the first example, and again, after you state what type of triangle it is, like I've done here, isosceles triangle, make sure that you state the reasons for how you're figuring out those parts. Okay, so folks, here we have example 2, and we're asked to find x. Okay, all right. So folks, in this one here, again, folks, I've said that I want you to identify what type of triangle it is, and again, folks, based on those congruency marks, all three angles are congruent. This is equilateral. Okay, it's an equilateral triangle. All right, and we know that it's equilateral because all equilateral triangles are equiangular. And the opposite of that is true as well, right? All equilateral triangles are equiangular, and the opposite of that is true. Or the converse of that is true as well. All equiangular triangles are equilateral. And folks, even if you didn't remember this corollary to the base angles theorem, or in other words, this little extension of the base angles theorem, even if you didn't necessarily remember this, that all equilateral triangles are equiangular, and all equiangular triangles are equilateral, then folks, then you could state also the base angles theorem, really. And let me show you how, okay? One or the other. So with that triangle that you got, oh yeah, okay, I didn't mean to put it upside down. Hold on. All right. All right, so with this triangle that you got, because you got three different, or in other words, this is really the converse of the base angles theorem. But again, like I said, I don't really have time to go into all of that. So for right now, just and for all my serious mathematicians watching, and I'm not saying that my students aren't serious mathematicians. Again, I'm saying again what is actually called the converse of the base angles theorem. But again, I'm not writing it here. All right. So guys, again, you can use. Since you got all three angles that are congruent here, it doesn't matter which two of these angles you choose to be the base angles for this equilateral triangle. But based on those two sides that they've got, I'm going to pretend, or not pretend, but like I said, it doesn't matter which ones you choose to, to say are your base angles in an equilateral triangle. I'm going to say that these two angles right here are my base angles. Like this right here is my base, okay? And even though all three angles are congruent to each other, but again, I'm gonna do it as if these two are the base angles. Again, so like I said, if you wanted to use the base angles theorem as your reasoning here, instead of the fact that all equilateral triangles are equiangular, okay, that's true as well. But again, folks, with the base angles theorem, or the converse of the base angles theorem, we know that if we've got two base angles that are congruent, then those two sides that are opposite from them, those two sides that are opposite from those base angles will also be congruent to each other. Okay. And this is really the converse of it, where it's, I said, I don't really want to put the word converse, but it's really sort of switching the whole statement around. But anyway, I said that's what it is. I'm gonna erase it, but that's what it is, though. It's the converse of the base angles theorem. Oops. If two angles are congruent, so again, folks, we know that if these two angles of a triangle are congruent, like what we see here, that means that the sides that are opposite to them are also congruent. So if one side there is 6, the other one has to be 6 as well. Again, folks, this is an equilateral triangle. All three angles are congruent, and all three sides are congruent, because equilateral triangles are also equiangular. Alrighty, so that means that x is clearly 6. Ooh, wow, where did he get that from? A hexagon? Oh, no, a pentagon? Okay, so this is example 3 here. All right, so it says find x. So again, folks, first thing I want you to do, the things that I need you to do in showing your work is tell me what type of triangle this is. And clearly this is an isosceles triangle, correct? Yeah, okay. Isosceles. All right, so this is an isosceles triangle. All right, our reasons behind being able to find out certain parts here. In this one, we're going to have to use two different reasonings for it. Of course, one of the reasons, or one of the little reasonings or logic that we'll be using is the base angles theorem. Wow. Okay, yeah, that's just sloppy. Ugh. All right, so again, according to the base angles theorem, if we got those two congruent sides right here, and the angles that are opposite of them are going to have to be congruent as well. So if one of these is x, that means that the other angle there is x, right? Okay, that the angles opposite of them have to be congruent. I'm not going to write out this definition of this again, but again, folks, it lets us know that these two opposite angles, those two base angles, have to be congruent. So if one of them is x, the other one has to be x as well. So folks, if that is true, and if both of these are technically x, then the next thing that we need to do, now that we know that, now technically that we've got all three angles, now we need to use the triangle angle sum theorem. Now that we know all three of the interior angles, 40 degrees, the x, and then the other x. That's three interior angles. So here's the triangle angle sum theorem, that all three of those interior angles have to add to give us 180 degrees. Alright, so all three of those angles, the x and this x and the 40 degrees, all three of the angles add to 180 degrees, right? Awesome. Lovely. Alright, so again, that's 2x plus 40. Subtract 40, we get 140, and then divide by 2, and we get that x equals 70. Oh, my bad. I'm tripping, y'all. Subtract 40. No, yeah. I did it. I just didn't say it. I mean, I said it. I just didn't write it the right way. Yeah, x equals 40. I mean, x equals 70. Yeah. I said all of the right things. I was just talking faster than I was writing. Okay. X equals 70. Okay. All right, so folks, here we got example 4. All right, and so in this one, they're asking you to find x. Again, let's do this. Again, the first thing I want you to do is list out what type of triangle it is. And these are both isosceles triangles here. There are 2 triangles there. Okay. All right. So, and then we can start listing out the reasons behind how we're finding certain things, how we figuring out and finding more information. What's our reasons behind all of that? All right. Boom, 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 boom. All right. First come first. The only angle that we're given in that diagram is that 110 degrees, so you got to use that to find out some other stuff. And that's an exterior angle to the triangle, but in this case we don't have to use the exterior angle theorem because we don't know two of the remote interior angles for that triangle anyway. But we can use the fact that this exterior angle is supposed to be supplementary with its adjacent interior angle. So these 2 angles right here, this exterior angle and the angle that's right beside it, they form a linear pair. Alright, so again, they form a linear pair. Which means that they are supplementary, or in other words, they add to 180 degrees. And so 110 plus what equals 180? That means that this angle right here has to be 70 degrees. Okay. All right, so that angle there, right there, has to be 70 degrees. Yeah, I really don't even like the way that looked, but guess what? It's going to be all right. Hold on one sec. Yeah. This angle right here. $70 degrees. All right, so we got that angle. Now we can use some other information that we know. All right, so now that we know that angle, The next thing that we got going on is here. Okay, again, we got these two congruency marks, and if we know that this angle is 70 degrees here, we can use that along with the base angles theorem. If we got these two congruent sides, that means that the angles that are opposite to them have to be congruent as well. So if one of them is 70 degrees, that means that the other one has to be 70 degrees. So this angle right here has to be 70 degrees. Okay. All right, so now that we know that that angle is 70 degrees, we can use that. And the next reason behind what we're doing, and again we used that base angle theorem to find that. Now we can use these two angles to help us find the third angle of this triangle using the triangle angle sum theorem. That all three of the interior angles have to add to 180 degrees. We use that to figure out what the third angle is in this triangle. The fact that 70 plus 70 plus that third angle, I'm just going to leave it blank for right now, has to be equal to 180 degrees. All three interior angles there has to be equal to 180 degrees. So again, we got 140 plus whatever that third angle is has to be equal to 180 degrees. Subtract 140 from both sides, and we get this third angle here has to be 40 degrees. All right. So now we know that this third angle here has to be 40 degrees. Okay. All right. From there, now that we got that, let's take what we know about that right angle symbol and the fact that we've got two complementary angles there, a pair of complementary angles. All right, so we got right angle symbol right there. I know I'm making that look probably even worse than what it do look, but it's okay. All right, so here now we got a set of complementary angles. Those two angles right there that are supposed to add up to 90. All right. And we know that this angle here that we just now found, that angle was 40 degrees. So if we know that part of it was 40 degrees, okay, that means that the other part, or that this other angle here, had to be 50 degrees. That means that this one here has to be 50 degrees. Because these two angles are complementary, they got to add up to 90 degrees. That's our reasoning right there. All right, so now that we got that this angle is 50 degrees, all right, now we can use that to help us find out some more information. Y'all see how this is going? We're using what we know to find out more information. Okay? And that's what we be doing. That's what we doing. Okay? Let me underline these. Yom, yom, yom. Okay, and then our next one, I hate to even do it like this, but you know what? It's gonna be all right. It's gonna be okay. Next from there. All right, so next thing is using what we know, what we just now found out about that 50 degrees there. Okay, so now we've got this other triangle that was right here. Yeah, okay, yeah, that don't even look. Yeah. All right, so now we got this other triangle right there, and we have found that this part here was 50 degrees. All right, and this angle there was x. Okay, so we a little bit closer to figuring out what x is, right? Okay, I apologize for those who are impatient about us not being done with this example yet. But again, folks, you see there's a clear logic to what we're doing. Okay, and you can't say that we're not showing explaining how we're getting each part of this. So, but anyway, yeah. So now we're in a position to actually be able to find out what x is, almost one step away. All right. So now at this stage here, we can use the base angles theorem again. Okay, because again, if we got these two congruent sides, that means that the two base angles, those angles that are opposite from them, should be congruent to each other. So again, if one of them was 50 degrees, that means that the other one is 50 degrees. All right. So now we know that this angle right here has to be 50 degrees based on that. And knowing that and doing that whole base angles theorem. Okay, and then guys, the very last thing that we need to do to find out what x is use our triangle angle sum theorem. And that'll be the last thing, because all three of these interior angles need to add up to equal to 180 degrees. Last thing, our last little reasoning here is the triangle angle sum theorem. Wow. All right, so again, we know that all three of those angles, the 50 degrees plus the 50 degrees plus the x, all three of those interior angles should add up to equal to 180 degrees. All right, these two, 50 and 50, give us 100. 100, when we subtract it, we get 80. And then that's what x is. All right, so folks, we did all of that so that we can figure out what x is. But we had to do all of that in order to figure out what x is. So again, I'm not doing anything that's not necessary. Okay, trust me. All right. So that is example 4. Okay, so here's example 5. All right, so in this example, they go ahead on and tell us right from the bat. They tell us that this one is an equilateral triangle. So yeah, so we ain't really had to put that. for again, my students enrolled in my classes at our school, where I'm asking you to state what type of triangle it is. The first thing that I need for you to show in your work for me, and then state your reasons for how you're getting each part. So again, folks, if we know that it's an equilateral triangle, then we know that all equilateral triangles are equiangular. Equilateral triangles are also equiangular. And if it's equiangular, guys, that means that each angle is equal or the same, right? And so, and we said that for an equilateral triangle, if each angle is the same, that technically means that each angle is 60 degrees. All right, and we had said again that if it's equiangular triangle, each angle is 60 degrees. So again, that means that this angle right here that says 2y, that angle is 60 degrees. Each angle there is the same if it's equilateral and equiangular. All right, so y equals 30. All right, and so then our next thing, since we know that it's equilateral, really, folks, with this one, with this one here, really you just need to know the definition of equilateral. Seriously, the fact that we're talking about a triangle that has where all three of the sides are equal to each other. I mean, literally, where you got equal sides, okay, or congruent sides. All three sides are congruent, which means that all three sides have the same measurement, right? Three congruent sides, or three sides that have the same length or equal lengths. So since we're talking about those sides having equal lengths or the same length, where they've got those side lengths there, the 3x plus 8. Again, we're saying that they got the same length, right? Oh. All right, so that means that this side, the 3x plus 8, should be the same or equal length as the 4x minus 4. And then all you got to do is solve for x right there. All right, so we already got y. All right, so subtract 3x from both sides, and you end up getting that all the x's on one side of the equation. Let me zoom out a little bit on that. Yeah. Boom, 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 boom. X minus 4. Add 4 to both sides, we get 12. Okay. All right, so that's example 5. Guys, I want to show you one or two more examples. Just different looking examples. Okay, so this example here is example 6. They want you to find x and y. All right, so here, in this one, guys, they do this one a little bit different because they give you the perimeter is 54 degrees. Sorry, the perimeter is 54. Guys, if you remember for a polygon, the perimeter of a polygon pretty much states the total distance around that figure, or in other words, where you add up all of the sides, right? The perimeter is the sum of all the sides, of all the side lengths, right? And so here we got three sides, and again, I just want to remind you of what perimeter is. Okay, it's the sum of all three of the sides of a triangle. In this case, since we're talking about a triangle, there are three sides. All right, so for this one is a equilateral triangle. If you weren't sure about that, then you would have been sure about it after you did your triangle angle sum theorem. It's isosceles, but it's also equilateral, this triangle. Yeah. If you do your triangle angle sum theorem, all three angles got to add to 180, 60, 60. That means that the third angle has to be 60 degrees there. Right, so that means the y is 60. If all three angles are equiangular triangle is equilateral, right? So that's where that came from. If you were wondering, well, how did you know for sure that it was equilateral? That's because if we know that all three angles are the same, it's equiangular, and any equiangular triangle is equilateral as well. Equiangular triangle is equilateral as well. So all right, so and then folks, what we know about perimeter, right? So use the definition of a perimeter, and the definition of equilateral, right? Well, first the definition of equilateral, right? If we know that one side is 4x, that means that all three sides are 4x. 4x, 4x, 4x. Because if it's an equilateral triangle, that means that all three sides are equal, correct? Alrighty, great. All three sides should have the same length, 4x, 4x, and 4x. And then, folks, if you use the definition of perimeter from there, then we can go ahead on and do what we need to do. Okay. That's an ugly asterisk, but you know what? It's going to be all right. All right, so if we know the perimeter is the sum of all three sides of a triangle. That's what we're going to do. We're going to add up all three sides, and they tell us what the perimeter is already. They tell us that the sum of all the three sides equals 54. So we set up an equation that represents that. Okay, so the definition of a perimeter says that when we add up all the sides of a polygon, we get that perimeter. So all three sides here, 4x plus 4x plus 4x equals 54. That's 12x equals 54. We divide by 12, we get 4.5. 4.5 or 9 halves. All right, so y equals 60, and x here is 4.5. All right, guys. Next, I just want to show you real quick what it would look like if some of your problems were word problems. All right. So in this example here, example 7, they don't give you a diagram. Hence a word problem, right? All words. If you wanted to draw out a diagram, you could, like especially if you know you're more of like a visual type of person that needs sort of like a little visual aid, or just want sort of like a little visual aid. Guys, they say here the measure of two sides of an equilateral triangle. Here they tell you that you've got an equilateral triangle, and all three sides are the same, congruent. They tell you that it's equilateral in this one. And they tell you that two of those side lengths are 3x plus 15 and 7x minus 5. 3x plus 15 inches, 7x minus 5 inches. All right, so guys, if we know that this is an equilateral triangle, again, folks, you use the definition of equilateral. The fact that all three of the sides are equal, or the fact that these two sides clearly have to be congruent or have the same length. Literally, the definition of equilateral, three congruent sides, or all congruent sides. Wow, that is not equilateral. That's how you know I is tired. Whew. All right, the definition of equilateral, again, folks, which means that we literally got all of the sides are the same length, congruent. So if you know that they're the same length, or equilateral, or equal lengths, right? Then you literally take the two lengths and you set them equal to each other for those two sides. Sides are equal length, right? That they're literally equal to each other, the lengths of those. All right, when we solve that, subtract 3x on both sides, you get 4x. Add 5 to both sides, you get 20. 4x equals 20. Divide by 4, you get 5 for x. Now, you're not done here. Why? Because they didn't ask you to find x. They said, what is the measure of the third side in inches? So guess what? If we want to find the measure of the third side, I suggest let's find the measure of any one of these sides, really. Because if this is equilateral, all three of the sides are the same length. So if we find one of these side lengths, that means we technically have all three of the side lengths because they're the same. Because it's equilateral. It's an equilateral triangle. So we plug in this value of x that we just found, and we substitute, doing that right there. All right, so let's substitute our value of x. 3 times 5 is 15. 15 plus 15 equals 30. So all three of these side lengths has to be the same length, which is 30 inches. So the measure of that third side is 30 inches, okay? Third side length, or the measure of the third side is 30 inches. All right, and then I'm just going to show you how to set up one a word problem that looks like what I'm about to show you in example 8. I'm not even going to work out example 8. Just going to show you how to set up a word problem that looks like that in example 8. Give me 1 sec. I got you. Example 8 coming right up. Right, coming right up. Example 8. Okay, so folks, here's example 8. Again, folks, as I said, I'm not even going to work this out. We're just gonna show you how to draw out the diagram here. Here it says in triangle GHI. So what does that mean? You need to draw out a triangle, any type of triangle, any triangle. Doesn't matter how it looks, whether it looks like what I just drew or looks like anything else. And I hate that this. Don't really hate it, but this thing here is making all of these triangles look exactly alike. But it don't really matter how your thing look. I'm going to leave mine looking just like that right there. Because it really don't matter how it looks. If you pay attention to everything else that they tell you, it don't matter how it look. It can look completely jacked up. It can look like that for all I care. I don't care how your triangle look. It can look like that, like a witch's hat. I don't really care how it look, as long as you got all of the pieces of information right about it. It don't matter to me how it look. Anyway, in triangle GHI, so if you got GH and I, don't matter where you put the G, where you put the H, or where you put the I, as long as you make sure you label the 3 vertexes, the 3 vertices, plural, okay, of vertex. As long as you make sure you label that, label all 3 of those, G, H, and I. Okay, so it says that HI, the length for HI, is equal to the length of GH. So that means that HI, that side length, is congruent to GH. Okay, so we know that we got an isosceles triangle. I'm not going to work it out, but again, I'm just going to finish labeling it and drawing out this thing, and then I'm not even going to finish solving it, just going to call it after we finish labeling what we need to label. Alright, 3x plus 4, it says the measure of angle IHG, remember folks, if you doing that angle, literally follow those three points like you're connecting the dots from I to H to G. So you know what? So you know which angle they're talking about. Angle IHG. Literally, like you're connecting the dots, those 3 dots from I to H to G. And now you know what angle they're talking about. If you didn't know before, now you know. (3x plus 4) be this angle here, and then it says, where we at? 2x minus 24 for IGH. Okay, IGH. Yeah, okay, that don't even look right, but it's okay. It's just based on the way that I drew it. So if you're talking about angle IGH, like if you literally connect the dots from I to G to H, you'll see what angle you're talking about. From I to G to H, it's talking about that angle. And it says that one is 2x minus 24. Guys, I'm gonna work this one out. I don't see why not. I'm gonna work it out. We're gonna work it out. And they say, what is the measure of angle HIG? So they want you to find the measure of this angle here that's missing. What's the measure of angle HIG? Okay. All right, so folks, if we're going to do this, it's isosceles. Then first thing that you're going to do as far as with your reasons is use the base angles theorem. The fact that if we know that we got two congruent sides, then those two base angles are going to have to be the same or congruent. Apologize about how sloppy it looked. I don't think my hand can, well, I ain't going to say that. Let's see. Ooh, that's sloppy. It's going to have to be all right. I tell you, it is going to have to be all right. Even if it don't look like the thing I drew out originally, it's going to have to be all right, y'all. So with the base angles theorem, because these two sides here were congruent, the two angles that are opposite from those two sides, or in other words, your base angles, wow, those two base angles have to be the same, congruent to each other. So if one of them was 2x minus 24, that means that the other one has to be 2x minus 24. Okay, so if you know that this angle here has to be 2x minus 24, again, now that we got all three angles, we can use the triangle angle sum theorem, because we know that all three angles inside of a triangle are supposed to add to give us 180 degrees. Triangle angle sum theorem. All right, so again, all three of those angles are supposed to add to give you 180 degrees. I'm going to zoom out a little bit more so I can actually have room to write out what I need to write out here. What's that? 3x plus 4 plus 2x minus 24 plus 2x minus 24. And all three of the interior angles add up to give you 180 degrees. All right, so then when we solve it out, combine our like terms, 3x, 2x, and 2x, combine those variables, that gives us 7x. And when we put the constant terms together, the 4, the negative 24, and the negative 24, we get negative 44. All right, and then from there, if we add 44 to both sides, we end up getting 224. And then if you divide by 7, we end up getting 32. Or at least I'm pretty sure that it's got to be 32. Because 7 times 30 gives you 210. And then 7 times 2 gives you 14. And when you add those two together, 30 and the 2, you get 32. And when you add the 210 and the 14, you get 224. So I'm pretty certain there, me being a mathematician, even though I ain't got no calculator on me, I'm fairly certain that that is correct. All right. All right, folks, that's all. I hope that this has been helpful. I'm tired. I got to go. I do hope that this has been helpful to you. Yeah. So again, that was example 8. Again, folks, remember that again, my students enrolled in my classes at our school, that for when you're doing the practice assignment for this lesson, that I want you to show your work in this particular way, that I want you to write out what type of triangle it is, and then I need for you to state your reasons for how you're getting each part, your reasons behind everything, okay? All right, because it takes being able to do this reasoning and think about it like that in order for you to even solve these problems. So, but anyway, that's it. I hope it's been helpful. I gotta go. Bye. 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 Sound like the M&Ms. Bye.